I'd rather insert it. I, C, select, S, X. It'll offer you a character. If I hit W, it'll say delete word. The arrow moves back and forth to give me feedback. My tracking spot changes. That gives me feedback. Now it tells me since it's an arrow that is armed, I can do something. We get a lot of feedback. Let me restore a view like this to show you. This is more normally the way we work with feedback up here. For here, I'm shown not working. That's an echo register that normally gives you the last 6 characters that you use. Oops, not working. All right. The last 6 characters and left shifts continuously, so you can look up at any time and see what have I just struck. And that's very good feedback. Here are characters that show me the different viewing parameters, view specs. They get large at times at which I can hit single strokes that change those view parameters. And each of those means something to me, and their being large at particular times tells me I can hit very quick abbreviation for changing the view. So I can say, all right, I'd like to go to produce, but I'd like to go to produce, they get big, I'd like to say one branch only, and let me look just that low, and I see it. Oh, I can say, I'd like to see one line only. I can see it. So these ways I move around, the way I get feedback up here, the way I use both hands to coordinate to tell the computer what command and what short literals I want, are all carefully designed to go together to make the repertoire We've talked about the devices and now the nature of the dialogue, or the kind of feedback we get from the computer for each of the discrete character strokes and actions that the user goes through when he's executing a command. So that system is really represented to a user by the repertoire of commands he has, by the function of each of those commands, and by the control dialogue he has for each of them. So they all together go in and making a design, and to do it well, you have to be very careful about the nature of the functions in that repertoire and the natures of the way they're controlled. So we've developed a very special language for talking with extreme precision about these control, both the command functions and the control dialogue for them. And a little bit later, when we tell you about the programming, Jeff Rulison will bring in some special examples to you of the languages we've used actually to program at high level these functions and the control feedback that we get in these control dialogue. But that's what we're going to call the control meta language in there. Let's see how we're doing here. Okay, let's move our little marker to say we've now gotten control techniques by us, and let's talk about implementation of our online system. I put over here a reminder. When I jump to here, I want the view below it to unfold in a certain way, so I've just told myself, hit those parameter specs when this is large, and then execute. And yes, I see that underneath I am going to talk next about hardware design and then software design, and that's going to be done by Jeff Rulison from Menlo Park. Hardware design inviting me to jump on a link here. Aha. He told me there wasn't such a thing as a link under there. Bring me back to remembering how I should have gone through this. To go down another level in hardware design, there are 2 features we want to talk about here to bring out to you the way in which we've gotten the kind of responsiveness and flexibility we need in this instrumentation environment. So way off in Bill English's file, Bill was responsible for the design of all of our hardware. There's an outline he made of the way the controllers work for the I/O controlling. Now from This line to the right are things that we added to a conventional SDS 940 system. And this is the swapping drum. It's got two buses accessing to four 16K banks. The CPU has one bus, and the peripheral equipment has another. And the good work of Project Genie at Berkeley, an ARPA project that evolved the 940 time-sharing hardware and software, produced a very neat priority system on this bus such that it can say, I'll defer my access to a given bank until the CPU doesn't want it. Or I'll defer it once or twice or three times, but then I really need it, so give me priority. And in that way, this bank can slip in many accesses to these while the CPU is hopping from bank to bank in its successive accesses. We've taken advantage of that to put all of our control out here, a large 96 million character Bryant disk for giving backup storage for ourselves, our two display systems, each of which drives 6 displays, and all of which are refreshed out of core, and the input controller, which samples the keyboards, the key sets, the mice of each station about 15 times a second, and our printer and the ARPA network coupling here all come in through that same priority basis. So they can all be working full tilt, and we find that we get very low interference in CPU cycles being interrupted or interfered with, something like a ratio of maybe 1 to 1.5% here that it can't get when it wants to, and this might be running 50, 60, 70% of the available memory cycles that it can handle. All right. The input controller stuffs it into core without ever interfering with the CPU's process, and then just interrupts the time-sharing system if there's something new and says, hey, take care of this user. And the display system reads out of core in from a tree structure-like set of links to cycle itself automatically and take all that material, output it to the display something like 15 times a second without any interference from CPU requirements. All right. So that system has allowed us to have one time-sharing computer take care of a lot of stations. Let me talk to you about the display systems, the other aspect of the things that we've built on here that are slightly unusual. All right, for that I'd like to switch to Menlo Park and get a view from a camera there and actually looking at the hardware. So these are the units that develop the displays. The computer constructs it right on a small high-resolution CRT, which you're focusing in on right now. And in fact, that's the CRT whose camera on the right, looking at it, is generating the text view that's being piped down here on my console. So as those are faded in and out between the two, you can just sort of compare them. So that's very nice. There's my mouse moving around in Menlo Park, my tracking spot. So our displays work with those being watched by commercial cameras. Look at my black bug. Commercial TV cameras, 875 line scanning rates, so they're fairly high resolution. Look at that. From there on out to the display station, the standard video microwave system. If we back up the camera shot a little bit, we'll see that we have a whole rack full of equipment here, serving 12 of them, but you'll notice quite a lack of cameras mounted on. We seem to have stolen them all for this show. So we only have several consoles that work right now because the cameras are mounted to give you these different special views. All right, there are quite a few advantages. We use this particular display system hardware technique pretty much as an expediency for an experimental system we had to build. We originally were going to build storage tube displays into here, but we couldn't get them delivered a year and a half ago when we really had to firm up our design. So we, as an expediency, went to this. Rand has been developing some very nice video stuff. They were kind enough to show us how these controllers and all would work with video. So we went ahead with this very simple brute force way of having the video signal generated by looking at a small CRT. Well, it turns out that that little CRT, its incremental cost, the video camera, the controller, and a monitor total about $5,500, which is cheaper than most fairly good resolution random deflection display monitors would be. So we come out well on the price of the hardware. Turns out that also that the cathode of the camera tube in just black and white usage like this, you can back off the scanning current of it so that it's a sticky cathode, so that actually it doesn't erase the image on it by each sweep. It may take 3 or 4 scans. And so with something like a 15 cycle a second refresh rate on those CRTs, the camera, the one that's generating this as well as the one we looked at it with a few minutes ago, have short-term storage in there. It's quite different from long persistence, but gives us the flicker-free display here, quite a flickery display there. This lets us use that display generation hardware for 3 to 4 times as many display stations as otherwise. You'll notice if we get just the text alone that there's a small effect by that bug smearing, but it's not that bad. And that comes from the memory in the Vidicon tube. Okay, so much for that. I'd like now to have us bring in Jeff Rulison from Menlo Park, and we'll switch to his console. He's sitting at one just like this, been working independently. Hi, Jeff.
Oh.
We're not hearing you very well.
Oh, you're not hearing me? How about now?
That's fine.
Okay.
All right. I'm sorry you can't see everybody here, but I can't very well either because of the lights. So we're about even.
Okay.
I'd like you to talk to them about the way the special languages have helped in making flexible design and study available for us of the user features, the functions and the repertoire of the commands, as well as the control dialogue for them. And then also, it'd be an interesting example here because you programmers are the ones who most intensely found use for working online as we're building up. Show them how you structured your system guide. Okay?
Okay. I think we can do that. We can get sort of a good feeling for the way the whole system is put together by looking through the system guide. The file is one that system programmers sort of put together, help them get around. NLS right now is getting to be a fairly large program. It's not huge by a lot of standards, but it's getting pretty big. This picture in our system guide file is a picture of the overlay structure. Our overlays are page sizes, so they're not too big in the 940, but each label in this picture names a code file, and each one is 3 to 20 pages long. I mean, 20 text pages if you printed them out. Just to sort of show how you can use a file like this to move around in the code, and also how the code is put together. As I said, each label in the picture is the name of an overlay, which is also the name of that file, but it also happens to be the name of a statement in this file. By selecting one of these pictures and moving there, I was going to do something for you to let you see better. What did I do?
Yeah,
we go back to the origin, start over again.
Bring back all the parameters.
There. Now let me move out. From the picture, I can move to a little section in this file, which is an area that system programmers leave around notes for each other. There's nothing much interesting here. A little bit about the documentation and the patch space that's left. Right from this spot, I can actually move out to the file. Suppose that I were going out in that control meta language Doug was talking about and just try to see, for example, the routines used in the delete word or move word. Let's go look at move word construct. I just select this link, and here is the file. This file is written in one of these many special languages that we've designed. So I just move down through it, find the move commands. Move, let's look here for move word.
You want to point out how you know it's move word?
Yeah, well, I was just going to look at that, Doug. As I was stepping down through that, I was sort of not only moving through the file, but the structure of the code is rigged in such a way that it's a description of a finite state machine. And so I was following the characters a person would type to execute that command. Down here underneath it, I see that the routine is QMW over in the overlay text edit. So let's go back to that other file. Move back to our picture again and find where overlay text edit is. It's right down here, so we'll go and sort of move down through that one. The text edit overlay illustrates a lot of the different kinds of things that we've done. This file has two major kinds of code in it. First one is many of these different special languages that we've built up. See, I'm trying to find QMW. That's right. It's down here someplace. There we go. Let's see. Oh yeah, it's the two kinds of code. This is still the kind from the other file, but the QMW routine, the first subroutine, the second subroutine that it calls, which is sort of interesting, is move word, or word delimiter, I'm sorry. This routine is written in our content analysis language, and it takes a text string and finds the definition of a word. It looks out for punctuation, and it finds any special blanks around it, and finds pointers that describe that word. Another interesting one is the next subroutine here. If we look at it, it's in another special language that we've built up. It takes the pointers left over from the delimiter routine and the text in the file and reconstructs the statement after the edit's been done. Let's see. Where was I in this file? The other portion of the file is written in the language that we call MOL. It stands for Machine-Oriented Language. The MOL is in a sense, it's a high-level language in that it has phrase structure and good control constructs like if statements and while statements, but it's also very, very close to machine language, 940 machine language. People talk about the actual registers of the machine, and you talk about doing indirect addressing. This language has helped us write the kind of fast, tight code that we want, that we have to have to operate in the time-sharing system, and at the same time, it's given us a lot of flexibility. It's also the phrase structure of the MOL designed to sort of mesh with the block structure of NLS. So here I've got a while statement. To see what's in that while statement, I can move down and see it's three statements, which is an if statement. The if statement is a single if statement, which has an if and an else part. And that whole block opens up to all of that. So by using the MOL like this, I'm able to move around very quickly in my MOL files. Also able to sort of zoom in and out of things. One of the, besides the sort of program organizational benefits that we get from designing all the special purpose languages, we've been able to design the syntax of these languages so that they fit with our linking structure and the conventions that we've set up and the aids we've built to help us in NLS itself to move around between them. One of the ways we've managed to implement all of these languages is by designing a compiler, which we call tree meta. All of our compilers are written in tree meta. I'd like to add that we're very thankful to some people at Systems Development Corporation for helping us get started on a lot of the notions in tree meta. Erwin Book and Val Shorey were just invaluable in helping us get started. By having all of our compilers written in a higher level language themselves, we've been able to change them all the time. So we're not only able to quickly modify the syntax of the control language for NLS itself, or the meanings of the commands by working in our high-level language, but we're also able to go in and just change the compilers as quickly as we have to accommodate all sorts of new hardware features and experimenting that we do like that. So in a system guide file, there were three sections. The first one served this program structure, and the picture and the fast links we looked at were sort of aids that the system programmers have built up to just move back and forth and leave notes. Second section here is on retrieval. I think I'll let that go for a while right now. The third section, more notes that programmers leave around about bugs, things that are wrong with our system right now. I got my blank line off. How did I? Well, anyway, one of the interesting things that NLS does, just an advantage of being online, is it keeps track of who you are and what you're doing all the time. So on these statements, on every statement that you write, it keeps track of who you are and when you did it. So not only can people leave notes around for each other, but sort of automated into how they, there's an automated aid here that tells us who did it and when they did it. I can set up search patterns. I think these will probably be talked about later. So that sort of summarizes what the thing looks like and how it's put together. Is there anything that I haven't talked about, Doug, that we were supposed to bring up?
No, I think you've
looking
been doing,
at my notes right here.
You're doing very well, Jeff.
Thanks.
You ought to see yourself with a 15-foot face.
I'd like to.
Great.
I guess I'll just turn it back to you then. I might add that people want to come up to our room sometime. We're more than anxious to talk to people about languages and metacompilers and all of the games that system programmers like to play. So I think I'll sort of turn it back with that.
Well, Jeff, how about going back to that place in the control meta language where you start down the dialogue protocol a person would use?
Okay. Right over here in main control.
Yeah. And off to another file where we're looking at real code now. And there's a branch of it down there.
Yeah. These top branches are all subroutines that are pretty meaningless, and it's WC means what case, and it's what's right. The person going to ask for.
So open that one level down now. Right. Now, all those things in parentheses that in NLS are the names of those statements are actually in the programming language that works here. The way it's identified, that's the character a user hits. If he hits a D, for instance.
A D here for delete?
Right there. All right. If he hits a D, that line tells you what the response is supposed to be. The computer's supposed to display certain material on the top of the screen. And then it's supposed to wait until the user does the next thing. Why don't you trim it to one line?
Yeah, I was going to do that. Why doesn't my branch only work? Oh, that's all that branch. Okay.
Hit EBT.
Well,
it's easy.
Okay.
I don't want to insult you by saying that it's easy to get a new view. Down there to say, all right, then if he's hit a D and it sets up what it says there, you can up one level below it, and that's the next block down in this special language, and you see, well, if after the D he hits something else like a W, it goes on from there to say what it is the computer's supposed to do in response. So this language here in its hierarchical structure, resembling the branching tree of choices user makes, specifying at every point what the computer does in feedback and the optional choices, and down in the end then specifying the actual function, like deleting a word. What's a word? And what do you mean by delete? And for what's a word, that's specified off in the subroutine he showed you in a special language to find in there what a word is. And it doesn't take a lot of programming skill to learn how to read these languages because they're at the concept level almost where the user wants to work. And so for us, in our experimental environment, our users are beginning to learn this so that we can look at that to find out how the system works and not at somebody's English text translation, unspecific though maybe. Well, Jeff, you did a great presentation, especially the last part.
Thank you.
Thanks very much. We'll come back now and I'll get my prop with my text and we'll go on to talk about some of the, oh, no, wrong text. Right day. Thank you very much. Well, remember that we were talking about hardware and software and implementation, and if we go all the way back, we see that we've finished control implementations, control techniques, and the implementation, and let's move our little marker down here to keep track of where we are. And we're ready now. I'd like to run through some of the ways in which we actually have use this. The programming itself represents a very good example for me, where following from the basic philosophy that concepts come in structure, and you'd like to structure your database, your information base that way, and have a tool at getting around it. I think that the way we've got our records for our programming organized, and then the special languages, using the hierarchy, using the names of places in there as labels of statements, so both NLS treats them as a name it can jump to. The compiler that compiles those files we were looking at treats those as the labels for those subroutines and procedures. It all makes a very nice way to study and integrate, and it's very powerful, exciting sort of thing to show. I hope people do come up to our open house and look at that. Let me go down here and open up under usage and say first some application examples. User documentation is a straightforward sort of use. If you were a user here and came and sat down early, you'd want to get familiar with this file. Let's go look. Dave Kasserus has written a user's guide. So down the hall in Dave Kasserus' office, in his drawer, pulling out the file, we go, and there you see it. The top view of it with the sort of the outline. But I'm interested in just showing this view very quickly. You want to find out the definitions of a lot of terms. Here's sort of a glossary. Well, let's do the thing called freeze a statement, and then say, put that at the top. Lo and behold, that statement now is going to be frozen in our display scanning windows from the dotted line down. And then we know about names and jumping to name, and so we can say, what's a bug? Oh, down here tells you what a bug is. I see. Well, let's see. What's a level? Select level. Tells you what level is. What's a mouse? That's fun to look at. There's a mouse. You can just point. So you can sit here and point to successive terms, and it goes there. The scanning window goes there. The frozen glossary stays, and you can see the definitions. Very nice. And some of the definitions you can recognize terms here. That's an odd one. Maybe that's a name. Let's just see. Oh, sure enough. It's a sketch showing the mouse and the mouse buttons. It's very nice to have documentation like this, and you as a user could sit down and early find your way around in this to find the definitions, descriptions, procedures for commands, and all like that. So let me go back to my guide and say, the next thing, you want to study or modify papers. All right. It happens to be that we wrote a paper for these proceedings. It's in the files. There it is, top level. Gee, it's interesting to study something like that. What does it have to say about user systems? Go to there, open up a level. I only want to see that branch. Oh, what about file studying? Open that up. Oh, specifications of form of view. What about that? Let's just open it all. Now I can read it. Gee, that's an interesting way to study. This material, incidentally, was organized for printing and printed out. And it's from this file directly we printed it out on the form we sent to the printers. And these things up in here, these three letters and equals, are special directives we embed in our text, so when the output processor does it, it puts in things like headers. Like this says, make the header on every page be D.C. Engelbart abstract. That's the prescribed form. The number between lines, double space it. All these others have characteristics. You get right justification, page numbers, all kinds of control on there. All right, so much for paper writing. Well, printout directives, I feel a little rushed for time. I'm going to skip that. That can show you a guide of all the directives for printing out. If you were a user, you'd want to go to that so you can have links to it. Joint file usage is something that is very powerful here. I went off to a file that we were working on as we were getting ready, the early parts of this presentation. And it was a message, it was something that three of us used a lot between us to coordinate the planning, task, contingency plans, the special needs in NLS for the fall joint, things like that. We developed a message technique so we could leave messages for each other. Under there are usage conventions, and let me just tell you about that. Underneath here, we direct messages to each other that we can unfold and see. But many times you didn't want direct messages as much as you just like to go through and leave a message for somebody. So we worked out that the conventions would be, where's an example? The convention we're going to use is that we would send a message to a guy. If I want to send Bill English, WKE, a message, I would put that in the file, WKE from DCE, with that pound sign in between. So any statement that's marked like that means there's a message to him from me. If I want to, I can say was also for Dave Evans, like that. So that's from me to both of them. All right, we have this thing we call a content analyzer, Jeff mentioned briefly, in which we can write expressions in a language. Let's just come down here and look. Here's a little expression in a special language that means I'm going to look for Mr. XXX, a message from him. All right, what if I say I want that XXX to be DCE? That says someplace in there I want to find that pound sign and DCE. So we've got a little compiler. We say from there, compile it. Comes back and says I did it okay. And now I can say, all right, only show me the statements that passed the test, that someplace in them they have that string. There they are. So in every one of those, that's from DCE, DCE. We go down there and look for it. How'd this one get here? This is to anybody from DCE. Then I can say, well, turn off that filter. How about for so-and-so? So I can say, all right, this is for WKE, a message for Bill. The rest of this pattern here says it's got to be followed by any number of commas and letter triplets, but eventually by a pound sign, or it doesn't go. Well, let's compile that and see. Okay, it passed the test. All right. There's for WKE, for him, and a dummy. Okay, so, well, it wasn't through searching. The thing about a time-sharing computer is that once in a while it gets being asked for business from other places, and if the response we want runs into a fair amount of computation, we run into other people who will bump us off to do it, and so sometimes it'll take a while to filter through all the patterns. With that content analyzer, sometimes now if I'm disabled slightly because this seems to be hung up in the wrong place, I'll have to run by the keyboard, and that's a real bag. You know, I'm so used to working with one hand and this that I can hardly remember what to do on the keyboard. Anyway, I want to go back to the file. The other guys at the other end of the time-sharing system are going to go in and see why, and I hope some hardware guys are too.